Hello, everyone. Good afternoon. I'll be discussing how we build next generation recommender systems with large language models. I'm Amey. I'm a machine learning engineering manager at Meta. Okay, a little bit about myself. I've been at Meta for a few years now, mostly working on Facebook video recommendations the last few years. Before this, I worked on Facebook ads as well as newsfeed ranking. In general, my interests are in recommendation systems, machine learning, personalization, and behavior modeling. Prior to that, I completed a master's at Columbia University in New York. So this is the rough agenda for the talk. We'll be going over introduction to recommender systems, looking into large language models for access, as well as some modeling paradigms for LLMs. Then we'll look deeper into how LLMs can be adapted for recommender systems, as well as industrial challenges and exciting future directions in this area. So this is, recommender systems are online systems mostly where users come either with an intent to query or just to discover relevant content. The idea for recommender systems is to generate user and item representations such that they can provide relevant content when the user needs. Once this content is provided to the user, they can interact with this content in different ways. For example, they could watch, if it's a video, they could watch it, they could like it, comment on it, share it with friends, and so on. So now, based on these interactions, we identify if a user is satisfied or not, and as well as like how much they are satisfied. And this can be fed into training data further on so that you optimize user satisfaction over time. So there are multiple challenges in recommender systems. There are multiple challenges in recommender systems, such as users' preference keep evolving over time. So this can be either on a longer time frame or a shorter time frame. And most of these preferences need to be learned through implicit feedback. What I mean by this is users do not give explicit feedback. Not everything you like, you will demonstrate it by liking the content. For example, if you don't like something, you could just skip over it to the next piece of content. So a lot of learning needs to be done based on implicit feedback. There is a large and diverse catalog often on recommender systems. For example, at meta scale, we have like billions of items in the repository with millions of items being added every month. Cold start problem is a real problem where we know very little about new users as well as new items that do not have a lot of interaction yet. We need to incorporate user context. That is, we need to really understand where the user is in their journey. For example, in the morning, you may be interested in watching short, snackable content, like short form video content. But at the night, when you're free, you would, probably watch long form videos or movies and so on. Next, we need to balance between popular and niche content. So niche content as well as creators need to be given an equal chance to be shown to users so that these creators and this content can thrive on the ecosystem. Recommendations need to be interpretable, that users need to really understand why they are seeing the particular recommendations and so on. So next, let's look into like large language models for recommender systems. Recommender systems have an extensive amount of knowledge encoded inside them. So you can think of them as a general purpose task solver. For example, they can memorize a lot of knowledge. They have ability to retain knowledge. As you can see in the question, it asks like, which country does Whitehall Township belong to? And the answer is United States, which the LLM is able to answer correctly because it has memorized a lot of knowledge. It's also able to understand and comprehend task objectives using very structured information. For example, in this question, you are given a particular context and a concept set and asked, what concept does this context refer to? And again, the LLM is able to get it right because it's able to make these associations very well. Next, tying this all together, it can apply this knowledge mostly through multi-hop reasoning. As you can see on the bottom, there's a question which asks, Jeremy Theobald and Christopher Nolan share which profession? So in this case, the LLM needs to really understand the professions of both these individuals and then find out the intersection set, which is able to do through reasoning. LLMs also demonstrate very powerful zero-shot and few-shot learning capabilities. They can overcome like common data sparsity issues of limited historical interactions. What I mean by that is, for example, to know that turkey is associated with Thanksgiving, a particular like recommender system would need to really understand like years of data to see that, okay, during Thanksgiving, you see a lot of instances of turkey associated with it. But in LLMs, all this information is encoded. And so with zero-shot or few-shot capability, it's able to like demonstrate this very well. This is a particular example. Like for example, if a cold start user comes in and asks for summer travel recommendations, they are served by these. They are served these recommendations like New Zealand, Santorini, Bali, Iceland, Barcelona, Peru, etc. And for example, the user selects the items listed in orange to know more about them. So based on this, the LLM is able to infer additional context. For example, New Zealand is famous for bungee jumping, Iceland for like caves or lava fields trekking. Peru has the Machu Picchu trail, so it really understands tying this all together that you are interested in adventure travel. So next time when you do come in the winter, it's able to show like relevant recommendations. Knowing that you looked into adventure summer travel, it's able to determine and show you places relevant to winter travel related to adventure. So in this case, like Norwegian Arctic coast, known for dog sledding, Patagonia, Banff National Park, Hokkaido is a place in Japan which is popular for like skiing or snowboarding and so on. It's able to also comprehensively understand user intents accurately and understand the user journey through these interests. This is not possible or very difficult actually to develop in traditional recommender systems which uses very abstract ID-based representations. So in this case, on the top row, you will see that this row represents art of photography, which it has already inferred on its own by looking at the videos in the sequence. So for example, these videos can range from, how do you earn $10,000 a month shooting real estate videography to, the mindset video about the mindset of a failing photographer. So, you can tie all these together to really understand this, all this whole consumption chain is about photography. Similarly, at the bottom, I don't know if it's very visible, but there are a lot of videos, not all of them mention go-kart racing, but you can understand from these concepts that it's all related to go-kart racing. And so we can build like user interest journeys and even understand users' interest journeys better. Next, we'll look into like modeling paradigms for LLMs and Rexes. There are mainly three modeling paradigms. So first one is using LLM embeddings along with your standard recommender system. So for example, you can use LLMs to generate user and item embeddings from your features and then use these embeddings in downstream tasks in your recommendation system. The next one is using LLM tokens along with the recommendation system. In this case, you can generate semantic tokens. Instead of embeddings, you generate semantic tokens from items as well as user features. And these capture user preferences, and then you integrate them in your downstream recommendation system stack. The next one is using LLMs as a whole. The next one is using LLMs as a whole as a recommendation system. So you don't have any other system behind it or in the later stage. You can directly use the LLM itself as a Rexis system. Here you give an input of the user's profile, items descriptions, prompt, and a task instruction, and then you get an output of a recommendation result. So these are the broad categories of LLMs. So we have discriminative LLMs and generative LLMs. Discriminative LLMs are like your encoder-only BERT-style models. These are typically used as embedding backbones for the downstream recommendation models. And the idea here is to align the representation of these BERT-style pre-trained models with domain-specific data through fine-tuning. There are various approaches here to do this. One is doing fine-tuning, where you have your pre-trained LLM parameters that you tune to data specific to these downstream tasks. And the second one is prompt tuning, where you don't have your pre-trained parameters, but you actually train the model by aligning the loss of the pre-training along with the loss of the downstream tasks. The next type of model is a generative LLM. These are very popular recently, like GPT models and so on. Here, the recommendation system itself is formulated as a natural language task, and you can use like prompt tuning, instruction tuning, in-context learning, and so on to generate recommendations. Techniques here involve like prompting and in-context learning. Prompting is where you design specific tailored prompts to actually enhance the effectiveness of the LLMs on the recommendation tasks. And in-context learning is where you give a few examples of this. If the input is A, then you have output of X. If the input is B, you have output of Y, and so on. And this is how the models can able to predict on unseen inputs without any parameter updates. In generative LLM, the next types are like prompt tuning and instruction tuning. These are both actually very similar, where LLM parameters are actually in prompt tuning fine-tuned to a particular task. In instruction tuning, the LLM parameters are fine-tuned to multiple tasks with different types of instructions. There's a lot of like ongoing work in this area. Just this is a snapshot from a paper citing all the recent works. Most of these works are post 2021, and actually you can see like majority of them are done in this year. So the pace of innovation in this area is like faster than ever before. Next, we'll look into how do we adapt LLMs for Rexis. So a recommendation system pipeline consists of various stages. The first one is user data collection, where you actually collect explicit and implicit data from user feedback on the recommendations. The next one is on feature engineering, where you transform your unstructured data into structured information. A feature encoder, where you generate embeddings that are used for scoring and ranking of content. And finally, the ranking technique itself, where you provide or you generate the output such that your items align with users' needs. So LLMs can be used across the stack. This is again on the right. You can see a snapshot of all the works where on each stage of the pipeline, how LLMs are used as demonstrated. So let's look into like LLMs for feature engineering. LLMs can actually take raw input data and generate some text output that can be used as features which augment the data further. So in this case, you can see that there are two tables in orange and in red, which are input to the LLM. LLM is able to generate some text from it, and it uses another secondary LLM to query this output and fix the output based on like if there are errors and fix it to generate. And then this is used to generate like features basically. So you have out of out of domain data sets, multiple of them. You can kind of combine these to develop outputs on the shared task, which uses all this data. LLMs can also be used to generate tags and model users' interest. So at the bottom, you can see there is a video, text, and an image there that the user interacts with. LLMs is able to generate very granular tags of what each of this is about. It's compared to the human-generated tags, which are again like very coarse. And so the tag GPT, which is generating these tags, can actually help to develop better representations of what users are interacting with and of user interests. Next is LLMs as a feature encoder, where you can add better representations of items as well as users for downstream tasks via extracting semantic information. For example, here you can see there are 4 news articles. All of them, most of them are related to movies. And given these, the model is asked what is the next item that the user would be interested in. And you can see in orange it's marked that all of these are kind of American-based content. But even though the model gets it right, that it's about movies, it actually shows information about Japanese movies, which may not be actually what the user is interested in. So the LLMs is able to capture all of this information and fix for this. LLMs are also able to achieve better cross-domain recommendations where the feature pools may not be shared. This is a good example here where on the top row you can see the Amazon grocery journey of a user where they buy Vita coconut water, lemonade flavor, and they keep buying it. Probably they liked it very much. They kept buying different flavors of it. So the LLMs are able to really learn these user behavior patterns. That is, if they liked drinks or snacks from a particular company, they may later purchase similar snacks or drinks with different flavors. So now you can kind of adapt this knowledge to different domains. For example, at the bottom is an Amazon pantry order sequence of the user. And so once the user orders tropical blend splash, the system is able to quite accurately recommend berry blend splash to the user. LLMs can also be used directly for scoring or ranking, where you can feed the LLM output into the final projection layer to get a score, and then sort the items based on this score. This is an example of the book GPT system. On the right, you can see is a big prompt that is asked. So GPT is asked that you are a professional book experience modeling expert. So it's providing a role to the LLM. Then it's saying that your task is to rate the books between 1 to 5. And in blue, there is an n-short prompt where it says that a user rates this particular book as score 5 and the other particular book as score 2. Based on this information, tell me what will the user rate these 2 new books. And it again asks the LLM to format the output in a particular way such that you give only 2 significant digits. And so this is a solution demonstrating how LLMs can directly be used to generate a final score that can be used in serving the recommendations. GPT for Rec is another system that was used for item generation, where there is a text format input saying that these are the items that the user bought. Please predict what will be the next item that the user will buy. And it's able to actually generate, for example, a makeup palette, which was never in the data set. So it's able to generalize and interpret user interests and information better. LLMs also are used for explaining recommendations, and we all know, we've watched Netflix. Probably we know that explaining recommendations makes it more persuasive, more transparent. You actually know why you are getting a particular recommendation, and you can also identify any errors very easily in these cases. So this is an example where on the right you can see LLMs was asked like a new movie Godfather 2 is recommended to the user given that they have watched Godfather, Shawshank Redemption and Pulp Fiction. Please explain based on this information why Godfather Part 2 was recommended. So it's able to craft very personalized and accurate explanations. And this is just an example, but this can be adapted to various other scenarios. So LLMs support like real-time user feedback, and can do bidirectional alignment if you have the reasoning of why you are seeing a particular recommendation. Next, we look into like some industrial challenges with using LLMs for Rex's purposes. The first one is training efficiency, where you generally have a large LLM size. Data is constantly expanding, like real world data keeps expanding over time. And most of these recommendation systems need very frequent model updates. So this combination is generally not great, especially from the point of efficiency. So people have proposed, fine-tuning LLMs using parameter-efficient approaches to get around this. Another way is to actually, relax your LLM update frequency. So keep the LLM constant for a longer time while you update the downstream recommendation system stack to adapt. The next one is inference latency, where most of these systems have a very few millisecond latency. But LLMs are known to have very high inference times. So you can either cache the LLM embeddings, use like distillation, quantization, or even just use the LLM outputs as for feature engineering only, and not in the inference stage. And the next challenge is on handling long text inputs. LLMs are known to have a very fixed or a very low context window size. And so they don't perform very well on large text inputs, which are very frequent in industrial recommendation systems. So systems that have been for a long time have very long interaction sequences of users and a lot of items and so on. So generally this is difficult for LLMs to adapt to. The next one is ID indexing. As I mentioned, like traditional systems have a lot of like ID-based features. And so, translating these ID-based information to semantic language has been difficult. So either you can like abandon these non-semantic IDs and use only the language information, which again then restricts you from using all the data. The other case is to introduce embedding-based methods and semantic information for the IDs, which is not super straightforward. Evaluation issues, I think they're popular. It was also covered in the last discussion. LLMs generally respond in improper formats, or many of the times they even decline to answer. So LLMs, how do you evaluate the recommendation capability of LLMs is an open question. Bias and fairness issues are also real here. Position bias is common because LLMs cannot capture behavior sequence orders very well. There is popularity bias issues, and there is also like fairness issues because they're influenced by sensitive data, sensitive attributes inside the training data. Some exciting future directions in this area. Like first one is hallucination mitigation. We all know like LLMs have tendency to hallucinate often. So there is work on using factual knowledge graphs as supplementary knowledge during LLMs training and inference. Making LLMs more safe and robust. That is, how do you make them less vulnerable to minor input changes? Now, we know that this is an open work area. This is not yet solved. Like this is, I think, one of the like big items that is being worked on currently. Building a unified benchmark is another theme here. So There is no standard evaluation to compare different LLM-based approaches. So how do you enable a very robust evaluation strategies as well as like cost-effective comparisons of different LLMs is something that is being invested in. And finally, vertical domain-specific LLMs. Here we need like LLMs that are tailored to specific industries, which offer like enhanced capabilities and personalization, like limited to the particular industry. So this is like all ongoing works here. So yeah, that's all for my talk. Thanks a lot. And if you have any questions, feel free to ask here or connect with me offline. Thank you.
I noticed that you discussed the inference time of LLMs. So which part of this is just pre-computed and stored in some key value store versus which part of this can be just implemented in like steady state real production traffic, that it can be part of the execution part?
Got it. Yeah, I think LLMs are being used in like different ways. So some of them is like using pre-trained things, but other ways are, for example, like augmentation. You can augment data, you can create a lot of like synthetic data. I think that's one very active way of using LLMs currently in production. But apart from that, just I think the inference time is like a very big blocker in directly using it. But there are like different ways that they are being used in like some non-time sensitive applications as well as in like augmentation in general right now.
Yeah, and just another question that you also discussed about the difficulties in evaluation of the success of the recommendations done by LLM. So, I mean, apart from the papers which are out there and the research going on, what do you personally think that just like our support lift confidence that we generally use to evaluate the success of any recommendation system? So, what do you think on the evaluation structure as of now, apart from those papers out there?
Like how do you evaluate the different models?
Correct. The success of recommendations done by LLM. So how do you evaluate them?
Got it. Yeah, I think right now the way most of these systems are working is like evaluation on the downstream tasks. So you incorporate LLMs rather than comparing different LLMs. I think directly because on the application side we kind of apply LLMs at different layers. And mostly I think industrial settings also prefer like open source models and so on, just for like data protection, privacy, all these things. But I think there are many open source models too. So generally these are evaluated currently on the downstream tasks, which is again not easy and also expensive in how do you evaluate.